Welcome to Number Theory. Today we are diving into a fascinating concept called the order of an integer modulo n. If you have ever wondered how digital clocks reset or how secure messages are encrypted, you are in the right place. We will build this from the ground up. So, let us get started. Now that we know our topic, let us build some intuition. Imagine you are running on a circular track, much like a clock face. But instead of taking normal steps, you are multiplying your speed by a certain number every single minute. Because the track is circular, you will eventually pass the starting line again. In mathematics, this circular track is called modular arithmetic, which simply means we only care about the remainder after dividing by the size of the track. The order of a number is exactly the number of steps it takes for you to land perfectly back on the number 1 for the very first time. Building on that circular track analogy, let us look at the formal mathematical definition. Suppose you have two integers, which we will call a and n. We require that n is strictly greater than 1 because a clock with only one position simply does not make sense. We also require that a and n are co-prime. This means their greatest common divisor is exactly 1. They share no common factors other than 1. This condition is absolutely mandatory. If a and n share a factor, your multiplications will get stuck in a subloop and you will never reach the number 1. If they are co-prime, the order is defined as the smallest positive integer that satisfies our core equation. This brings us to the mathematical formula that defines the order. The equation states that a raised to the power of k leaves a remainder of 1 when divided by n. Let us break down every symbol here. The letter a is the base number we are multiplying by itself. The letter k is the exponent, representing how many times we multiply it. This k is our order. The symbol with 3 lines means is congruent to, which is a formal way of saying leaves the same remainder as. Finally, mod n tells us the size of our circular track, meaning we divide by n and only keep the remainder. As k increases, the powers of a cycle through different remainders. But the order is specifically the very first, smallest positive value of k that makes this equation true. Before we move on to any complex proofs, let us see this formula in action with a concrete example. We want to find the order of the integer 2 modulo 7. This means we are looking for the smallest positive power k such that 2 raised to the power of k leaves a remainder of 1 when divided by 7. First, we must check if 2 and 7 are co-prime. The only positive number that divides both is 1, so the mandatory condition is met. We will calculate the powers of 2 sequentially. 2 to the first power is simply 2, which leaves a remainder of 2, not 1. 2 squared is 4, which leaves a remainder of 4. We still have not reached a remainder of 1, so we must continue testing the next powers. Continuing with our calculation, let us test the next power in the sequence. 2 cubed is 8. When we divide 8 by 7, it goes in exactly 1 time with a remainder of 1. We have finally found our target. The modular equation is satisfied. Since 3 is the strictly smallest positive exponent that results in a remainder of 1, the order of 2 modulo 7 is exactly 3. Physically, this means the powers of 2 will repeat in a cycle of 3 forever. If you ever need to find a massive power like 2 to the power of 300 modulo 7, you know the remainder will just be 1 because 300 is a perfect multiple of our order 3. To make this even clearer, let us look at what this cycle actually looks like on our circular track. The diagram you are seeing visually represents the cycle we just discovered in our first example. The numbers 0 through 6 represent all possible remainders when dividing by 7. Starting at the highlighted number 1, multiplying by 2 moves us along the arrow to 2. Multiplying by 2 again moves us to 4. And multiplying by 2 a third time brings us perfectly back to 1, completing the loop. Because it takes exactly 3 jumps to complete this loop and return to the start, the order is 3. This visual loop is exactly what modular arithmetic represents. Now that we have successfully used the formula and seen the visual loop, let us understand a crucial theorem about how the order behaves. The theorem states that if a raised to some random large power h leaves a remainder of 1 modulo n, then the order k must perfectly divide that exponent h. Let us prove this step by step. We start with the division algorithm, which is just the formal mathematical way of saying division with a remainder. We divide our large exponent h by our order k to get a quotient q and a leftover remainder r. The standard rules of division tell us that the remainder r must be greater than or equal to 0 and strictly less than k. We then substitute this expression for h back into our modular equation to set up the next stage of our proof. Continuing our derivation, we can now analyze the exponent in terms of the order k. Using the standard rules of exponents, we break apart the addition in the exponent into the multiplication of the bases. This gives us a to the power of k all raised to the power of q multiplied by a to the power of r. Now we use what we know. We were given that a to the power of h is congruent to 1 modulo n. We also know from the very definition of the order that a to the power of k is congruent to 1 modulo n. By substituting the number 1 in place of a to the power of k, we drastically simplify the expression. This substitution is the key mathematical reasoning that will reveal the true nature of the remainder r in our next step. Let us bring this proof to its final conclusion. Since the number 1 raised to any power q is still just 1, that entire term vanishes. We can drop it entirely, leaving us with a beautifully simple relationship. 1 is congruent to a to the power of r modulo n. This tells us that a raised to the power of r leaves a remainder of 1. But wait, we define the order k as the strictly smallest positive integer that makes this happen. Since our remainder r is strictly less than k, the only way this equation does not contradict our fundamental definition is if r is exactly 0. If the remainder is 0, then h equals q times k. This proves that the order k perfectly divides the exponent h. This is a powerful tool because it limits the possible values for the order. So we have proven that the order perfectly divides any exponent that yields a remainder of 1. This brings us to a very practical problem. Testing every single number to find the order can be incredibly slow for large numbers. Thankfully, we can use theorems to speed up our work. Euler's totient theorem provides a powerful shortcut. It tells us that the order must be a perfect divisor of Euler's totient function, represented by the Greek letter phi. The totient function simply counts how many positive integers less than n are co-prime to n. By finding this value first, we drastically reduce the number of calculations needed because we only have to test the divisors of phi rather than guessing blindly. Let us apply this shortcut to a new example. We want to find the order of 3 modulo 10. First, we verify that 3 and 10 share no common factors, so their greatest common divisor is 1. Instead of testing powers one by one, we calculate Euler's totient function for 10. We count the numbers less than 10 that are co-prime to 10. Those numbers are 1, 3, 7, and 9. Since there are 4 such numbers, phi of 10 equals 4. According to our theorem, the order must be a divisor of 4. This means the order can only possibly be 1, 2, or 4. We have instantly narrowed down our search and will now test only these specific powers. Continuing with our narrowed list, let us test the possible divisors. The first power gives a remainder of 3. Since 3 is not equal to 1, the order is not 1. Next, we test the divisor 2. 3 squared is 9. Dividing 9 by 10 leaves a remainder of 9. This is still not 1, so the order is not 2. The only remaining divisor of 4 is 4 itself, so we test that next. 3 to the fourth power is 81. When we divide 81 by 10, the quotient is 8 and the remainder is exactly 1. We have found the smallest power that satisfies our condition. Therefore, the order of 3 modulo 10 is 4. Physically, this means the powers of 3 repeat every 4 steps. You might wonder why anyone cares about how many times you have to multiply a number to get a remainder of 1. In the real world, this concept is the absolute backbone of modern digital security. Every time you send a secure message, log into your bank account, or buy something online, your data is protected by encryption algorithms like RSA. These algorithms rely entirely on the fact that finding the order of a number modulo a very large prime number is incredibly difficult and time-consuming for computers. If a hacker cannot find the order, they cannot crack the code to read your private information. Furthermore, the order dictates the repeating length of fractions when converted to decimals. Without this fundamental property, the secure internet would completely collapse. We have covered a lot of ground today, so let us review the key takeaways. First, the order of an integer modulo n is simply the smallest positive exponent required to reach a remainder of 1. Second, this concept only works when the base number and the modulo share no common factors. They must be co-prime. Third, visually and physically, the order represents the exact length of the repeating cycle generated by multiplying a number by itself. And finally, we proved that the order will always perfectly divide any larger exponent that also yields a remainder of 1. You now understand the mathematical foundation that keeps our digital communication secure. Great job working through these concepts.